We've done probability, although this had a different picture last time. Physics of the everyday, as opposed to physics of the sometimes. Science essentials, that might be interesting. Let's see, calculus done right, as opposed to when I do it, then it's called calculus done wrong. I use those jokes every time we do this stream. Quantum objects, I don't think we've done quantum objects. Or quantum, we have to do quantum something. And it's either going to be the computer board or it's going to be the cat that's like playing with the universe. And I really want to do the cat in the universe, okay? We also we can learn how to program with our snake friend here. If you can, I don't know if you can read this on stream, but it says print and it says hiss. We could do coding at some point, maybe not tonight because this one's going to take a while. Like I don't have an aptitude for programming, unfortunately. So this one may not be as good as you're thinking it is. There's going to be a lot of typing. There's going to be a lot of reading. So there's not going to be a lot of like visual. There's not going to be a lot of questions about crib death in the one about Python, okay? There were questions about crib death in the chapter on probability, though. That's kind of fucked up. And yeah, let's start the course. When things get small, things get weird. That's like when you have a wiener that's so tiny it actually goes inside. When things get small, things get weird. Oh, start course. Quantum objects, spin class. I think I know where this is going. Take a bold first step into the weird world of quantum objects by building the laws of quantum physics from scratch using simple experiments. You do not want me doing that. That's not, What you'll accomplish. Death. It's 3.68 rotogens per hour. It's not great, but it's not terrible either. Dr. Rockywitz, you shoot the N-word. This radiation box says, I'm going to do it. I'm going to say the N-word. How could parts of a room get dimmer when you open a second window in the sunlight? I don't know. The guy who built the house is dumb. You opened regular Magic Unicorn. You opened the dark window. It sucks out the light. See, it's just that's how quantum works, okay? The quantum window that doesn't let light in. It just lets light out. In everyday life, the objects we encounter and interact with tend to follow certain rules. As a result, our brains are wired with an internal logic for how we expect objects in the world around us to act. A tennis ball thrown against the wall will tend to rebound in a predictable fashion. A laundry hamper full of socks, when paired and sorted by color, will remain paired and sorted forever. Not if you have a cat, which there's one down here, so those socks better watch out because their days are numbered. You want a good gamer analogy for quantum physics? It's the silly race from Marble Madness. Everything you know is wrong. And the ball goes up. How do you explain that, huh? Next page. There is nothing new to be discovered in physics now. All that remains is more and more precise measurement. This quote is often misattributed to various preeminent physicists, including William Thomson, the first Baron of Kelvin, in the closing years of the 19th century. The true quote is a bit different and reads, "The future truths of physical science are to be looked in for the sixth place of decimals." Are to be looked for in the sixth place of decimals. Would you only calculate to 5 points? Quiz 1. They're giving us a lot of like preliminaries on this. They haven't asked us any questions yet. The most common way to begin studying quantum mechanics, the physical laws which describe microscopic phenomena, is to follow its real-world historical development. The story often starts as early as the double-slit experiment. The double-slit experiment showing the diffraction of light in 1801. I prefer the double-slit experiment is like, hey, would you rather fuck the Velociraptor or the T-Rex? Basically, the double-slit thing, it was something where it was like, there should have been an even distribution or something with there's two slits and they're passing atoms through it, and it either goes in one or the other. But it went through both, and people are like, Why? Why won't you ask me a question? We're gonna, like, go through the... You only get, like, the first chapter as free. To question the quantum cat, you must first question the quantum cat. Okay, we're going to fast forward to the quantum revolution and instead begin with an experiment from 1922 that exemplifies the behavior of quantum objects better than any other. We will start by experimenting with a purely quantum property, spin. So, basically, spin, the way spin works, I'm not going to read this, I'll explain it real quick. Basically, certain subatomic particles should be spinning in one direction, but the problem is that until you observe them, they're technically spinning in both directions, which is something called a superposition, where it's occupying two states simultaneously until it's observed, which is the philosophy behind Schrodinger's cat. Was this a helpful explanation? It's not the... Yeah, okay, see, it even... The Schrodinger equation. That's what we're getting into. So let's skip ahead. I mean, we finished the quiz. Are you going to ask me some... Did you like this quiz? I guess I did, because I got 100 for showing up, but you didn't ask me anything. No! Well, we didn't get any... Hang on. Because we observed this quiz, it turns out it didn't ask us any questions. But, until it was observed, we answered 50 of them. But... with the observation we made, there were no questions. And Brilliant's trying to get some money out of me, so I guess we're going on to the next category. And this is going to be a very weird upload on the YouTube channel because there's no questions in the quiz. So I guess... Yeah, I know where the premium button is. It's right up there in the fucking top, I guess. So unless we can continue. It looks like it'll let us continue, actually. Hang on. Okay. I know. Okay, good. We do have some questions here. Understanding how neutrons behave suddenly sprang to the attention of physicists during the Manhattan Project when it became obvious that neutron transport was critically important for moderating nuclear chain reactions in nuclear power plants and atomic weaponry. Uh-oh. The single N-bomb. Let's start a bit more simply and consider the behavior of a single neutron. A single neutron is generated from a sufficiently hot nuclear oven. Sufficiently hot. Cranked it up to 450,000 degrees, you know. Put that chicken in there, get it nice, and you gotta turn it every once in a while. Perhaps as a product of fusion or fission. This neutron exits the oven through an aperture and travels into view. What kind of path do we expect from a ballistic neutron? Okay, so the options are gravity will rapidly pull the neutron to the ground, drag will slow the neutron rapidly, the neutron will continue on a straight ballistic trajectory. Okay. Rocky, one Jimmy Neutron is created in a croissant oven. Okay, so I don't know why I have this pen, because I'm not writing anything down. But, so we've got, like, this whole thing, there's, like, a bomb here, and they're nice enough to inform us that it's fucking, like, uranium-235. Great. Okay, but what I know, okay, it's good, you got, basically, okay, I don't know nothing about radiation, alright? I mean, I know a little bit. I actually read about this kind of shit in my free time, because it interests me, but I don't understand it. I just read about it, and I'm like, oh, okay. Hey, HBO's got a special about Chernobyl. I think I'm going to watch that. So, okay, let's not... And this is not a box. This is a gun. And this is a bullet. And I know that when you shoot a bullet, eventually gravity will pull it down to the ground. So I'm going to treat that the same way. Neutrons have weight. They're not weightless. Even if the weight is that much, that's still weight. Alright? And gravity is still going to pull at it at 9.6 meters a second, or whatever the fuck the pull of gravity is. So I'm gonna get yes. And that's incorrect. Actually, the neutron just keeps going. Completely disregards gravity. Did not even know that. Did not even know that. The foundations of classical mechanics are still intact. We expect the ballistic neutron to behave much like a fastball or a bullet would in zero... Well, then I guess I fucked up. But it does say in zero gravity as predicted by Newton's first law. So we can... We can neglect the force of gravity on the neutron for experiments, since gravity's acceleration is vanishingly small compared to the velocity of a hot subatomic particle. But what about one that's not as hot? What about one that's like more like a 3 or a 4? Does it weigh it down? The neutron will tend to follow a straight trajectory at a constant speed and direction unless acted on by an unbalanced force. So, basically, it ignores gravity because it's stronger than gravity. That's scary. Let's introduce a complication. We arrange two permanent magnets of opposite polarity to generate an inhomogeneous magnetic field, B, directly perpendicular to the path of our neutron through space. Given our understanding of classical physics, how might we expect our neutron to be affected by the magnetic field if we treat it as an uncharged point mass? Okay, so knowing what I know about when things get small, things get weird, it's gonna blow up. It's gonna fucking kill everybody, okay? You don't put that on a magnet. No one knows how those work. The trajectory of the neutron would bend toward the north magnet pole. The trajectory of the neutron would be unaffected by the magnet. I'm gonna lock that one in real quick. Or it would bend toward the south magnet pole. I'm gonna say maybe it's moving too fast for the magnets to give a shit. Also, 87% of people got that right, so it's not really cause for celebration. Oh no. They're playing Dr. Mario between the magnets now. Fuck. A spinning neutron with the magnetic moment S couples with the magnetic field, much like a tiny magnet. Depending on its distance from the apparatus, the magnetic field B, will change. The interaction between the magnet and the magnetic field also depends on which direction the magnet is pointing. Some orientations lead to an upward deflection, others cause downward. The interaction energy between a spinning neutron or a tiny bar magnet and a magnetic field is given by USB. Did you guys fucking set that one up on purpose? How would the deflection force caused by this interaction change if a tiny bar magnet or a spinning neutron were flipped 180 degrees, pointing up, pointing down? That's the drawing. You take the whole thing and just turn it upside. How? How would you do that? How would you flip the neutron upside down? You got a little tiny thing. You just go beep, and you do like. How would you do that? Is it hypothetical? How do you flip a neutron? How do you get some tweezers that tiny, the kind that you use to grab your dick with? Because when things get small, things get weird. Regular magic when you do it carefully. Okay, roughly half the original deflection force. Roughly 1/4 the deflection force, or an equal deflection force in the opposite direction. Okay, I'm going to say it doesn't change. You flip it around, it doesn't matter. Basically, what I'm starting to learn here is that the correct answer is nothing happens. Fucking big brain. That's right, Rocky. We got it. We're already like, I don't understand this shit. The force. And if the axis of spin S is in the same direction as B, then the dot product, the dot product, isn't that what GoDaddy sells? Is positive, and the force pushes the neutron into regions of higher magnetic field. That's my favorite. Was that Steve Winston? Higher Love? Was that him? Fuck. Anyways. However, if S is in the opposite direction as B, then the dot product is negative, pushing the neutron in the opposite direction. If we place a particle detector on the opposite side of the magnet, we can measure the magnitude of the neutron deflection, giving us an indication of which direction its spin is deflected. Okay, Rocky, do I look like I know what a dot product is? Do I look like I know? It's funny that there are only 4 forces in nature. I don't know, magnets, gravity, Star Wars, and the police? Are those the 4 forces? How do you expect this new neutron to be deflected by the magnet apparatus? Down. Because that's the thing. That's the experiment. That's the double slit experiment, where it should have been one particle should have been going through, but it went through both. So it's going to be even. It's going to look like it went both ways. That's what it's going to be. Oh, it'll be random, I guess. Never mind. I don't know shit about quantum anything. Okay, let's turn up the heat in the thermonuclear oven generating our neutrons. Let's not. That's how you do bad things, okay? When the Russians did that, a lot of people died. Okay, so this is asking, what do we expect from a constant stream? A localized, a continuous flat distribution, or a continuous distribution centered around no deflection? So if it's going to be, if the deflection is supposed to be random, then it should trend toward just being a flat distribution on both sides, right? How are you supposed to get these questions right? I feel like I know everything you know is wrong. When things get muy pequeño, muy... What's the word for strange in Spanish? I don't fucking know. Why is this happening? What's so special about neutrons that they have to be quantum while bar magnets and baseballs happily follow classical expectations? Well, baseballs, there's more ingredients. There are, okay, you got one neutron by itself, right? Okay, boom. Bar magnets, everything is neutrons. Okay? There's neutrons and all sorts of shit. Bar magnets, but you got the protons in there too. And there's also electrons. And that's it, right? You get to get the whole package. Same with the baseball. Okay? It's a bad analogy, because there's more shit in here than just the one neutron, okay? Do not use that to answer a test question. You will get it wrong. We choose neutrons for our case study because classically they shouldn't be affected at all by a magnetic field, but they are deflected in the strange binary way because they have a quantum property that we call spin. At the human scale, objects composed of extraordinarily large numbers of microscopic quantum objects, including neutrons, protons, and electrons. So that's what I just said. Why don't we observe the binary quantum effects of spin in macroscopic objects? Because baseballs don't. That's the answer. Because baseballs don't. The answer choices are macroscopic objects don't obey quantum mechanics. Spin can't be observed using macroscopic instruments. Or quantum effects fluctuate and tend to average out in macroscopic objects. Rocky, Draco had a doctorate dissertation. Well, ladies and gentlemen, it's come to my findings. Thank you for gathering to this lecture. I am deeply thankful for you and all the support I've had throughout my years, getting my masters of quantum, my doctorate and masters of the universe of quantum. And it is my conclusion, my findings, that it's because baseballs don't. Thank you. No further questions. No further questions. Okay, quantum is like when it's small, okay? It's small. The world around you is magic. You still believe in Santa Claus. When you get bigger, when you get macroscopic, when you get older and bigger, you know it's bullshit. So macroscopic objects don't obey quantum mechanics because it's too big. We know better. I know not to exist in two places at the same time. There's not two of me sitting on this couch alternating one frame at a time, okay? That's not happening. It's probably the last question. Quantum effects fluctuate and tend to average out in macroscopic objects. But wouldn't that be some scary shit if it didn't average out and the baseball did instead of don't? That'd be weird. So I'm gonna say it's probably this. It's yeah, only 69 got that right. Nice. So that's why you don't teleport around. The reason why you don't teleport and exist in multiple places at the same time is because your body has averaged out. We don't do that. But statistically, there might be some outliers 6 sigmas away from a standard deviation where there is somebody who's just trying to get through the day and they're like, ah! he's teleporting around. And he's probably on disability. That's probably a disabling condition. He's probably on the dole, and he can't go to the bank because he tries to hand someone the check, and he just goes through. He puts it through him because he's not really there. Only extremely precise measurement of isolated quantum objects can observe the effects of spin. The strength of the neutron spin magnetic moment is about 10 to the 34th power times lower than the strength of bar magnets you're used to. This is why quantum mechanics was discovered by a bunch of tenacious physicists who were obsessed with the details past the 6th place of decimals. I guess that makes sense, but it doesn't, because everything I know is wrong. Sure, that was a great quiz. Hit continue, and we'll go back to the courses here. Okay, so that was quantum objects, and we quantum sucked at that. Regular Magic Unicorn. Sounds like a bunch of nerds. Sounds like you need to get laid. Thanks for checking out this video. Leave a like if you liked it, leave a dislike if you didn't. Either way, your feedback is appreciated. And you can also subscribe to Gatorbox if you like this content and want to see more of it from us. Catch us live Friday nights at 9 p.m. Central at twitch.tv/Gatorbox. If you'd like to support this channel, you can do so at patreon.com/Gatorbox or streamlabs.com/Gatorbox.